In this set of videos, we are going to look at the topic of hardware co-simulation. In particular, we are going to see how two of the tools that we have used so far, Verilator, which is one of the tools that can be used for Verilog simulation. Some of the things that we have done before were with iVerilog, but Verilator is yet another Verilog simulator. And Renode, the tool that we have been looking at in the past few videos for how to do emulation, can be combined together to do what's called a hardware-software co-simulation. Right? This is not exactly the same as what's called a hardware-in-the-loop simulation. It's a co-simulation because what we are doing over here is we have a simulation of the hardware and the system that is sort of emulating the processor on which the software is getting emulated, and we are sort of integrating the two together. So once again, there is this confusion regarding the term, should it be simulation, emulation, co-simulation, what are all these things? For the most part, we don't want to get too bogged down in the terminology. As discussed earlier, Renode is generally thought of as a system level emulator. What Verilator does is Verilog simulation, right? It sort of literally is trying to sort of go through the process of compiling the Verilog netlist, or rather the Verilog code, down to an equivalent set of functions which can then be evaluated. Now, why would we want to do something of this sort? Let's look at that in a little bit more detail. So, the goals for us are going to be to understand the workflow involved in doing a hardware co-simulation and look a little bit into how Verilator works. We are not going to go into any level of detail out here. At the first cut, all that I'll say is Verilator is a Verilog simulator. That's pretty much all that we need to know. But what is important over here is how Verilator works, because that actually influences how we use it. Right? What Verilator does is it takes Verilog code and converts it into a set of C++ libraries, which means that effectively it's taking your Verilog code and converting it into a set of functions or classes or modules in C++, which finally get compiled into an executable, a software executable that can run on the processor. In doing so, it brings the notion of time. It effectively emulates the concept of time in the C++ code by actually just bringing in a variable which keeps track of the time, right? And what that means is that because it is able to compile into a set of C++ files and therefore create a library that is in software, we can then integrate that into the Renode system and do an emulation where one part of the Renode platform that we are building is going to be a co-simulated peripheral, which means that whenever we want to sort of see how whenever the AXI bus, for example, tries to communicate with that device, Renode has the ability to basically go out there, activate that peripheral, get the data back from there, and then feed that back into the emulation and continue on its way. Right? And what we will do is, eventually what we want to go is to actually get this running on real hardware. But right now what we are going to do is we are going to focus on validating the hardware with two types of software interfaces. One is the bare metal interface and the other is the Linux based driver and the platform driver based interface. So let's go a little bit deeper into all of these steps. Right? So first things first, what exactly do we mean by hardware co-simulation, right? Co-simulation refers to the process where we run real hardware, that is an RTL simulation, alongside the system emulation. So even though I say running real hardware, this is of course not yet running on an FPGA board. So it's a simulation of the hardware, right? It's a Verilog simulation. Now in pure emulation, what we would do is that, let's say I wanted to add a new kind of peripheral into Renode, I would need to create some function that behaves similar to what that particular peripheral is going to be. Now the Renode code itself is written in a language called C#, which is related to C and C++ but is different in its own ways, right? But has all the same kind of behaviors. In particular, it compiles down into native executable code, which means that whatever stub that you are writing over here will execute very fast. And we have already seen examples of this. For example, the Renode REPL files, the platform files, have things called UART, they have things called timers, they have the various memory blocks, right, which we used to sort of create a fake smart timer and a fake FFT and so on, right? All of those are actually modules that are written in the C# language of Renode and compiled in such that as far as Renode is concerned, it just becomes a function call and does a pure emulation of the entire system. It's very easy to set up. The problem is it may differ from how the real hardware works. In other words, you have written some Verilog. If there are bugs in the Verilog, for example, there is no guarantee that the stub that you write in C# is going to be the same. In other words, they are different languages, they are different models. You are rewriting this stub completely separately from the Verilog, right? So it's not guaranteed that they have exactly the same behavior or the same kind of bugs. Now that's as far as pure emulation is concerned. What we are talking about now is co-simulation, where what we are going to do is write real Verilog, RTL, right, register transfer level, which means that we intend it to be synthesizable, and we are going to simulate this via this simulator called Verilator. And one restriction that we have over here is pretty much it has to be more or less synthesizable code. We do not do the arbitrary kinds of Verilog or system Verilog constructs that may be used for Verilog test benches. We are looking primarily at the synthesizable code, and Verilator has sort of a subset of code that it can actually simulate effectively, right? Verilator has an interesting approach to simulation. What it does is it basically compiles your Verilog code into C++. You then put a wrapper around it, which is itself written in C++ in most cases, and it allows you more control than if you just try taking the basic Verilog test bench and running it. Now, what all this means is that since you are actually simulating the Verilog code that you have written, it is accurate in the sense that it is at least accurately modeling whatever RTL you have written. What that also means it is typically much slower, and the reason for that is because a stub model is just emulating the functionality, whereas over here we are sort of going cycle by cycle and trying to accurately model the behavior of every single step of the process of the running the Verilog code, right? So it naturally tends to be slower but is more realistic in general, right? And very often we do want to go for this idea of co-simulation before we actually go into hardware. Part of the reason is because we are now able to do a full system level emulation with the actual RTL that's going to run on the system, right? So there are a number of scenarios where that actually becomes quite useful to have. So just to go a little bit deeper into why we would want this co-simulation at all, in the traditional development flow there is a gap between hardware and software development, right? What happens is you typically have two teams, there's a hardware team and a software team. The hardware team's job is to design RTL, synthesize it and put it onto an FPGA. The software team basically sits here waiting, right, until the hardware team is more or less done. Then at some point they basically, once they have a reasonably detailed specification from the hardware, especially once all the the register maps and so on have been clarified, they can write the driver. But now if they write the driver too early, once again they wait, because the designing and debugging and synthesizing the RTL typically take quite a long time, right? So you can do that, but this ends up becoming sort of a bottleneck, right? And finally, when you want to debug on the hardware, it turns out that unless you have done both of these, so in other words, it doesn't matter if you finish synthesizing and putting it on the FPGA, unless you have a driver, you cannot debug on the hardware, right? So given the fact that the synthesis debugging process can typically take quite a long time, we would like to see, is there some way that we can break this bottleneck? What co-simulation allows you to do is to say, okay, the hardware team continues, they design the RTL and they do a simulation, they build a simulation using Verilator. Well, Verilator is one of the tools, that can potentially work with other Verilog simulation tools as well, right? Meanwhile, the software team, as soon as the basic specification in terms of registers and so on are frozen, can write a driver. And now interestingly, because of the Verilator simulation, they can now test in a platform like Renode, which allows you to start testing as soon as the hardware team has some Verilog that they believe is on track, right? So even before they sort of do all the synthesis and optimizations and any modifications for speed and so on, the functional simulations and testing can be done more or less in parallel, which means that both teams are able to work more closely together and finally putting something on an FPGA or whatever, even for an ASIC kind of design, can presumably work faster. Now of course over here I have mentioned a few things such as FPGAs and Renode and Verilator, which are very specific to the flow that we are going to be using here, but similar kinds of flows exist even in industrial settings with a different set of tools, right? The idea of co-simulation goes well beyond just using Verilator and Renode together. So what exactly does Verilator do? It's a Verilog simulator. What it does is it starts off from RTL code, your .v files in Verilog, and it essentially runs a command, right, which says, okay, I need to call a C compiler and generate an executable. And what you do is that typically you need to write a wrapper code which says, okay, you take the Verilog code, convert it into C++ modules, right? So it generates some kind of cycle accurate model of your C++ code. So always blocks, for example, are converted, sorry about this thing over here, but anyway, the always at blocks that are present in your Verilog code get converted into functions in C++, right, which essentially cause the advance of some kind of an internal simulation clock. So you are writing a C program, right? Effectively Verilator does that work for you. It creates the notion of a C program inside which there is a number, right, some maybe an integer variable or something which keeps track of a so-called simulation clock. And what it does is always blocks are converted into these kind of functions which are related to the notion of the simulation clock. Every kind of bus transaction or anything else that you have where there is a posage clock is going to change the value of that simulation clock, right? And effectively, in other words, it is able to take all your Verilog code, convert it into C++, combine it with some wrapper code that either you write or in some cases it can be generated automatically, and create an executable which you can actually simulate, right? So CocoDB, for example, works very well with Verilator. It's able to generate the wrapper for you. It basically takes in the Python, it takes your Verilog code, does all the things nicely behind the scenes and gets a good simulation going, right? Now, as far as we are concerned, the good thing is this same executable that is being generated out of here, out from this Verilator code, can also be compiled into a so-called shared library, which means that Renode can now link against that. Renode is a regular software program running on your host wherever you are doing your simulations or emulation, right? And what that means is if there is a shared library with certain functions that have been compiled using a language like C, then I can make those functions available to Renode by linking it internally. And what that means is at some point Renode can be made aware that if it needs to use something called a smart timer, it needs to call these functions, right? So all of that can be handled very neatly. As far as Renode is concerned, the module that you write ends up looking like a peripheral that you can then use. Okay, so yes, the fact that Verilator basically automatically introduces this notion of a simulation clock and converts your Verilog code into a set of functions which handle both the Boolean evaluation as well as advancing the clock is what allows us to integrate with Renode. So at a high level, the architecture, what is happening over here is that inside our so basically we have our entire Renode emulation, right, which basically is emulating an ARM CPU with a bus, in our case an AXI bus, which in turn is connected to memory. I'm calling it a DDR memory, but as far as Renode is concerned, it just says it's memory, right? You will notice that it doesn't really differentiate between dynamic RAM or static RAM or anything of that sort. As far as it's concerned, there is a sys bus, a system bus, which in our case we treat as an AXI bus, and which is connected to memory and which is also connected to a bunch of peripherals. We have already seen things like the UART and the timer, and this week we are going to basically look at another new peripheral which is an FIR filter, right? Now the interesting thing is, as we will see, when we want to bring in this co-simulation, we will have a Verilator interface which creates a .so, a dynamically loadable C library, right, which connects to Renode. So this part of it basically is internal to between Renode and that function library. What that means is at this point this entire blue block that I have over here corresponds to what's happening inside the Renode emulation, and what it means is that my Linux code, the VM Linux, the kernel that I actually compile, will end up running on this entire system. Remember that Linux doesn't just run on a CPU, it runs on a system. It needs access to the memory, it needs access to the peripherals, things like the UART where it can output its messages and so on. Otherwise, just a CPU by itself without even memory, it makes no sense to talk about it running an operating system, right? So this is roughly where what the integration looks like. This Verilator interface is what we will be creating. So now there are a couple of things that we need to keep in mind over here, right? There are effectively two separate clock domains when we are trying to emulate a system like this. One is that Renode has its own notion of internal virtual time. What do I mean by that? It's the emulated system clock, right? Keep in mind that when I'm running a operating system like Linux on a CPU, I need to have a notion of time because Linux is a time sharing, time multiplexed system, right? What that means is it's a multitasking system which uses the fact that it can basically multiplex between different programs sufficiently fast, right, that it can make you believe that all of those are running concurrently, or rather give you the impression that they are running at the same time, right? So it has its own internal notion of something called a system clock that is required so that, for example, the timer interrupts go there, it is able to context switch between multiple different programs that are running and so on, right? But the interesting thing is, I don't necessarily need this to be related to the actual clock that is there in my system. And what I mean by that is, remember that I am emulating my entire platform, which means that I am actually running all of this code. Renode is running on my x86 processor, but it is emulating an ARM processor, right? So what it does is, along with sort of emulating a different instruction set, it also says, okay, you don't really need to know whether 1 microsecond or 1 millisecond of time, whether it actually passed in the real world, right? I will let the program know when a certain amount of time has passed, and based on that the program can make its decisions, because typically that's how operating systems work, right? If there is no instruction that needs to execute at a given point, it will basically say, okay, let me sort of go to sleep and step forward by some number of microseconds or milliseconds or something like that. So managing that time can be done independently of the real so-called wall clock time that is happening in the outside world. Now we also have yet another simulation, which is our Verilator simulation, right? Now once again over here we have a cycle. This is cycle accurate because I have always had posage clock kind of constructs in my RTL code which tell me what to do at every edge of the clock, right? In Renode, for example, it doesn't really care whether your CPU is pipelined, whether there is a pipeline stall. All of those things are not really modeled at that level of accuracy, right? It just sort of makes sure that it's functionally correct. It needs to execute the operation corresponding to each instruction. Whereas the Verilator simulation has to be cycle accurate. Every single step, every always at posage clock has to be evaluated properly. Now the point over here is, this is also a simulation. As you might have already seen, you might say that your Verilog code is running at 100 MHz clock, right? You generate a clock of 100 MHz, but the speed at which it gets evaluated internally may not be 100 MHz. It may be effectively only able to generate something like 100 kHz toggle rate for the clock, right? It depends on how fast your processor is and how complex your design is, your Verilog design, okay? But the interesting thing is, in most cases, what we are trying to do is, we have a Verilator peripheral which is talking to a Renode platform through the AXI bus, right? And what that means is that we are primarily interested in bus accesses. And therefore, we could also give the Verilator simulation an artificial slowdown clock, right? And basically tell it, okay, work with a clock of like 100 kHz or 1 kHz or 10 kHz, right? What's the advantage of that? It allows Renode itself to run much faster than this. And the reason why that becomes important will actually become clear once we actually look at the co-simulation. If I try running my Verilator code at 100 megahertz, effectively what it's saying is that if I am trying to emulate a 100 megahertz CPU over here, for every tick of the clock, every instruction, I need to go through and evaluate my entire Verilog code, right? And that becomes terribly slow, right? Instead of that, if I say that, okay, look, maybe I'll take a choice and say that for every, let's say 100 clock cycles on this, I'll evaluate my Verilog code once. Functionally, we are still okay because the interaction between these two sides is happening through the bus, right? And as long as the bus transactions are modeled correctly, the speed difference does not really matter. It may matter at some point, or rather this kind of difference will matter only if we were somehow trying to do an exact cycle accurate match between what is happening in Renode and what is happening in the whatever peripheral that we are creating. But if you want to do that, you should actually be running a Verilog simulation of your CPU itself, because that's the only thing which is guaranteed to actually give you that level of accuracy, right? Renode is not really meant for those kind of things. So as we will see, there are two separate clock domains: Renode's virtual time, which is basically trying to emulate the behavior of a CPU running at 100 megahertz, right? And there is a Verilator simulation which is running at some other clock frequency. And if I try setting this to high, 100 megahertz itself, it means that for every tick, every instruction being executed on the CPU, I need to go and evaluate my entire Verilog code once more. Instead, if I say that for every 100 ticks over here, I'll evaluate this once, my system should run much faster, okay? And we'll see an example of that as we go forward. So the interaction between these two is basically that bus transactions cause advances in both clocks. And that's the nice part of the bus, right? It very cleanly sort of separates out this notion of the clock from the bus. It's effectively giving you a separate kind of a handshaking interface between two different devices, right? And what we can say is, if there is a bus transaction, let's say that, on the AXI bus there is a read or a write or something of that sort, I know that my Renode itself needs to advance by a certain amount, right? A bus transaction has been activated, and on my hardware side it will take me some amount of time. I can basically advance the time and say, okay, now it has moved forward to so much, right? Now what usually happens is I model the AXI bus such that if I am trying to read from a given location or a given address, my Renode will just freeze for that much time until it gets the data back. So it's not as though the Renode says, okay, this is taking 1000 clock cycles, let me execute 1000 instructions. It just waits until it actually gets the data back, which means that functionally you are still fine. Your hardware effectively gets activated only when there are bus transactions, or at least you can get a close approximation to that. Whereas your Renode, when there aren't that many bus transactions going to your co-simulated peripheral, can actually run much faster, right? So both of these ultimately mean that there is no dependency on the wall clock. The wall clock literally means the normal time that you and I know, right? That we look at the clock and see, okay, how much time has actually passed. Both of these clocks, the Renode virtual time as well as the Verilator virtual time, are internal to the respective systems.